The next type of continuous distribution that we're going to talk about is an exponential distribution. And exponential distributions have been found to provide pretty accurate models of how customers get serviced, the time it takes for service, for example, in many different types of businesses. Whether we're talking about customers in a drive-through lane at a fast food restaurant, or customers inside a bank dealing with tellers, or customers at a retail establishment going to different checkout lines, airline travelers going through the security checkpoint. All of those are situations where we have customers that are being served, and they almost always follow an exponential distribution. The exponential distribution looks like this. It doesn't look like our bell-shaped curve. It looks kind of like the bottom half of a C. And in many ways, it's kind of the exact opposite of a normal distribution. Because with our normal distribution, we saw that the vast majority of our observations are going to fall right in the middle, very closely bunched around that mean. But with an exponential distribution, we find that there are a lot of observations that will happen very quickly. There are a lot of others that will take a long period of time, and there are very few in the middle. Very few in the middle. Okay? So, we have an exponential distribution calculator in StatCrunch, and it works similarly to the normal distribution calculator, except we don't have to worry about a standard deviation with an exponential distribution. The only thing that we have to worry about is the mean. What is the average time that it takes to be served by this process? And your book uses the Greek letter theta to represent the mean of an exponential distribution. So if you see in your book or in a problem in the homework where it's talking about, oh, well, theta equals 10, that means the mean for that exponential distribution is 10. If it's referring to theta, that essentially is 0 with a line in the middle, that's a good indicator that it's an exponential distribution. All right, so we'll go to Stat and Calculators, and then we're going to choose our exponential calculator here. You can see our diagram does have that look of the bottom half of a C. And let's say that we're talking about an example where we're going through an airline security checkpoint. Let's say that the average amount of time is 12 minutes for somebody to get through that checkpoint. Now, one of the things that we have learned with respect to a normal distribution is that if the average is 12 minutes, then half of the values are going to be below that, and half of the values are going to be above that. Let's see what happens with our exponential distribution. If we're looking for the probability of being below 12, below the mean with our exponential distribution, it ends up being way more than half. 63%, close to the 2/3 of everybody who goes through that checkpoint is going to get through well under the mean. In fact, if we looked for 10 minutes, even something that's quite a bit below the mean, we still have almost 57% getting through 2 minutes shorter than the average time. Then you're going to have people like me who have a fake knee and always get pulled aside. And you're going to have to go through the wand or the extra pat down, and it's going to take longer. So you're going to have a percentage of the people who are going to end up taking quite a bit longer than the mean. Let's look at the probability that it will take us longer than 20 minutes to get through. Let's say we've got half an hour to make our flight, and we know that it's going to take 10 minutes from the point that we get through security till we get to our gate. We got to get through security in 20 minutes or less. So what's the probability that we won't make it? What's the probability that it's going to take us more than 20 minutes to get through that checkpoint? And you see that even though 20 minutes is well above that average time, it's getting close to double the average, we still end up with right at 19%. Almost 1 out of every 5 people are going to take more than 20 minutes to get through that checkpoint. That is a definite characteristic of exponential distributions, that you have a large percentage of people who are going to get served very, very quickly, much shorter than the mean, and then you still have a reasonable percentage that are going to take longer than the mean. We can also find the probability of being between two values here. We click on the between button up there, and it's just like we saw with the normal distribution. If we wanted to know the probability that it's going to take somewhere between 10 and 20 minutes, let's say, we find that that's 25%. Now, just to make one point kind of clear here, we looked at the probability that it would take less than or equal to 10 minutes to get through, and we saw that that was 56%. We've got the probability here that it's going to take somewhere between 10 and 20 minutes to get through, and that is 25%. And we also saw the probability that it would take more than 20 minutes to get through, and that was 19%. And guess what? If you add up those 3 percentages, it is not a coincidence that that equals a total of 100%. It's got to, because we've actually looked at all possibilities. No matter how quickly you get through that checkpoint, you're going to fall into one of those groups. Either you were less than 10 minutes, you were somewhere between 10 and 20, or you were more than 20. So that's got to add up to 100%, and that is not a coincidence at all.